Well, good morning, everyone, and thank you for joining us. Welcome to today's webinar titled Rotting Roofs, Causes, Mitigation, and Code Requirements. My name is Brett Borth, Director of Business Development here at Braun Intertech, and I'll be your host for the morning. Before we get into the presentations, I want to tackle a couple of housekeeping items. Everyone on the show today will receive a follow-up email that will contain the recorded version of today's webinar, along with a PDF version of the slide deck. CEUs will come in a separate email within a week. We will have a question and answer section at the end of the webinar, but would love to hear from you during the presentation. To do so, simply type your question into the question box. So without further ado, I'd like to introduce today's speakers. First at bat is our very own principal architect, Mr. Steve Flayton. He is joined today by Mr. Gary Patrick, Executive Vice President of InSpec, and Mr. Scott Futrell, President and Founder of Futrell Fire Consult and Design. And with that, I will hand it over to Steve.
Thank you for attending the webinar on rotting roofs and their causes and mitigation. I'm Steve Flayton from Braun Intertech, and we put this presentation together because we saw a need that was appearing in the industry to get the word out to everybody. So we're doing this quickly. If you have additional questions, please feel free to contact any of us in the future. So the program is going to go through some of the comparisons of code required assemblies of roof sections where we have things like apartment buildings, townhouses, condominiums, and so forth. They're using wood frame attic spaces or trusses or low slope roofing, whatever you'd like to call it, that has been filled with fiberglass insulation instead of using the fire extinguisher or fire protection systems like sprinklers in that concealed space. And it has been causing some difficulties with rotting of the roof membranes or the plywood, as you can see in the upper right-hand picture here. So today what we've got is Scott Futrell from Futrell Fire Protection, and Gary Patrick, Executive Vice President of InSpec. We've all gotten together here and looked at this. The program came about because I got a call from Scott Futrell about changing from a sprinkler system to fill in the cavity with fiberglass, and he was looking to have the fiberglass tested. Well, that kind of led to the unintended consequence of changing the dew point in the assembly, which would have led to deterioration of the roofing. So some of the history that we have here, back in 2000, the IBC came out and offered this option of filling the cavity instead of with a fire protection system, using a blown in fiberglass to kind of squelch the fires that may take place or not provide the oxygen that was necessary. What's happened here is the vapor retarders aren't continuous. Some of the air barriers from the interior to the exterior are not continuous. And we'll show you some of those voids and openings that have led to things. And that moisture from the rich, warm interior, particularly with housing, gets up into the attic space and condenses, causing this rot. It's a problem that's pretty prevalent here in the northern part of the United States. We're not sure exactly how far it's going down and other people are seeing, but you can rest assured about halfway down to the deep south that there's a transition point that this won't be as big a problem. So the problem again is the proper placement of the vapor retarders. When we've got the fiberglass insulation, the dew point comes way down into the actual attic space. If your vapor retarder normally attached to the ceiling, as we've seen in all sorts of these buildings, has any penetrations or bypasses in there, it creates a source of moisture that gets in. And it's really more the air diffusion, the air bypassing rather than the diffusion of the moisture that's causing the problems. Part of the thing we're trying to do here with the seminar is also get you used to understanding more about dew points, get into a little bit of research on it on your own, learn about that, learn about the WUFI modeling, which will help take your local weather conditions into account over a 5-year period and look at how the moisture may continue to build up in the systems. The failures we're seeing of these roof decks is occurring anywhere from 2 to 10 years after completion of the building. We're going to see a lot more of them. There's more and more of them showing up every day. And in this community where we have a lot of these buildings being built with this type of detail, we anticipate seeing more of the growth in these problems. So there's also an understanding of the sprinklers and the concealed spaces and what will and will not work. We see with all the insulation going in that you can create an area where the heat won't get to the sprinklers and can cause some frost and breaking of pipes. We've also seen where the system is put in but not necessarily completely detailed, and with the lighter gauge piping we have shorter lives to some of the sprinklers. So you've got to explore the options of both of these systems. Again, the vapor retarders are never perfect. We've got the sheet poly that seems to be the leader because of the cost. However, several inches of foam can be used as a vapor retarder as well, and that will allow you to help seal some of these voids, get into corners which you otherwise can't do with the plastic sheet. Areas that don't get covered are things like this, where there is voids that in the framing that the poly came up on the left side of the opening, right side of the opening, but around in the middle there were a bunch of studs that formed a chase at a bathroom area, and that area had nothing in it and was allowing air up into the attic space. The same thing on the right hand side, which is formed off of a firewall using resilient channels in the sheetrock location, is kind of underneath those two plates that you see, and that air can chase up through that cavity into the attic space and also cause issues. So one thing that you also need to think about as we're looking at it, and I'll go back to this previous one on the bottom where it says original construction is different than repairs. Well, normally we try and get the building dried in and get the roof in on top of things and then do everything from underneath. We can't necessarily do that in the repair of some of these buildings because we'd be in everybody's units tearing the ceilings out. So instead, we do a repair from the top side by pulling off the plywood, pulling out the insulation, and spray foaming those areas to get that air barrier back in place. So let's talk briefly about dew points. A dew point is where air has got enough moisture in it that it's saturated, it's 100% relative humidity, and it won't hold air or moisture any longer, and it condenses out on the various surfaces. That dew point that's calculated, we'll show you how to approach that, is on the outside of your vapor retarder. So if you have a roof section in which you have a vapor retarder on top of the deck, that dew point needs to occur outboard. So you have 10 below outside, 70 degrees inside, somewhere in between the two will meet. If it falls on the inside of that vapor retarder, you will have condensation in the building, which is what's causing some of these problems. So try and learn more about this, learn how to use psychometric charts, which we'll show you shortly. As mentioned, the diffusion through a 4x8 sheet of gypsum board here reduces about 1/3 of a quart of water per heating season out into an attic or wall system, whichever you want to look at. However, you punch a 1-inch square hole in that, and it produces 90 times that volume of water, or 30 quarts of water out in that capacity. And wood does not have a tendency to absorb that without causing damage. Here is a cross section, as we mentioned, where the dew point is, and over on the left, you can see the left bottom says 57.5 degrees Fahrenheit dew point. That's outboard of where the vapor retarder is, so this we would not anticipate condensing. However, you have to look at it for maybe even a broader temperature range that may get down into the sub-zero temperatures, and that dew point can still move around. So learn how to do these type of things in calculations, get a consultant that can help you do that, whatever is necessary to make sure you understand all of those conditions. So a psychometric chart has this general form that we see here. Along the bottom, you take your dry bulb temperature, which is essentially your interior temp, run vertically till you hit that little round spot, which is intersecting with the humidity, relative humidity curves, and there are several of these curves that you'll see in the next image. And then you go directly left horizontally until you hit the outside saturation line, and that is your dew point. It's that simple. So here is one of those things. If you look at the, call it 80 degrees inside, run up to 50% relative humidity line, and out to the left, you're going to be in the 50-degree range, roughly, for relative humidity when you're going to have dew point occurring. So we're going to go through some case studies here to show you how some of this started. Originally, we started seeing problems in some parapets because of the sort of balloon framed exterior walls that would allow air up into those, and it would condense up in the top and cause rot. Well, this has now been moved down further, and it's the same kind of problem. It's just a much wider parapet. Some of the modes of failure, we're seeing some of these failures, doesn't make any difference whether it's a white roof, a black roof, mechanically attached, fully adhered and so forth, they're all kind of problematic. So this is what we start to see in the failure modes, where the roof deck is deflecting enough that it's holding water, adding weight to it, deflecting even more. And as the condensation is getting in there, the roof deck is essentially rotted. You can just walk on the roof membrane and there's not much structural stability underneath it. Some of these areas of parapets where you have the kickbacks in order to support some of these taller parapets for architectural detailing are also areas where air can come in through those cavities up through the walls and then also diffuse out through the roofing system. Different methods of monitoring for moisture. This was a area where the roof membrane was peeled back. The device on there is a Tramix meter that measures kind of a voltage between two pins to give you a moisture content. And even this was running at a high moisture content, and you don't really see standing water on it. This was directly below it as well, and the roof deck looks fine, but it was at an elevated moisture content of about 20%. Here's another example of a stairwell wall. So you've got the two layers of drywall there, and the air is getting up and underneath this. You can see that the roof deck is totally rotted here, and there's air bypassing all around this up under the deck. Another location where the membrane has been pulled back. The piece of plywood that you see there was not what was there a year ago in October when it was opened. That plywood was added, and by May of this year, so October to May, that piece of plywood has gotten mold on it, and it is thoroughly saturated with the air that's been bypassing into the attic. So next I'm going to turn the presentation over to Gary Patrick from InSpec to talk to you a little bit more about some of the WUFI modeling and some of the detailing that needs to take place.
Thank you very much, Steve. Appreciate the introduction. InSpec's been involved in about 3 evaluations, investigations on these failing roofs in the past 6 years. They too are in the central Minnesota area, multifamily residential buildings, apartments, condos, townhomes. Roughly 10 years old is what we've seen. We've seen a little bit less than that, 8 years on a couple projects as well. But as Steve was pointing, I was talking to Steve earlier that he's seen a couple now in the 2 and 3 year range, which is kind of shocking to hear. In our cases, we had wood open truss roof construction and all of the assemblies. And on the right is a graphic that shows from top down kind of what these assemblies look like. As Steve mentioned, the types of roofs we've seen too are, it doesn't matter what type of system, it's a conventional roof system. Not having a vapor retarder, there was no vapor retarder in the roof system. We had OSB or plywood deck, and then this concealed space, 20, 24 inches where the truss is at. It's shown and depicted by this light gray color on the slide. And of course, that space is not ventilated, it's not sprinkled, it's filled with cellulose or fiberglass insulation. This drawing is showing over a separation wall, which kind of depicts a couple of other things that we're going to talk about in a minute about vapor retarder consistency and thoroughness. But symptoms for these projects, not a lot going on as far as leakage, no water entry coming down from the roof. A little bit of ceiling mold was picked up on a couple of the projects inside at the interior walls, from interior to outside walls to ceiling. But the most interesting thing, the most telling thing was that there was deck deflection under foot traffic. Technicians were up on the roof doing some field work and noticed it had some soft spots, and felt that it was definitely deflecting more than it normally should for a roof system. So of course we jump into action to start doing test cuts, destructive test openings on both the top side and from below. And this photo shows the ballasted single ply membrane pulled back. And as you can see in the upper side of that test cut, there's a fracture line, and that's of the cover board that's deflected down, caused by the deck that's deflecting and fracturing below that. So when this gentleman stepped in this area, not this guy cutting it, but one of the operators on the roof doing some maintenance work stepped in that area, he felt this compression, and that's what we opened up. So further opening that up, we see there's a lot of deterioration going on. The plywood, actually OSB deck in this case, dropped down into the truss space itself. And as you can see, there's a lot of moisture in there, a lot of mold, deteriorated OSB. The top cord of the truss is deteriorated. There is corrosion happening with the metal tie for the cord components. So a lot of damage going on there. That certainly is not what we want to have. Inside, we're looking at similar conditions once the ceiling sheetrock was taken off. Wall sheetrock was removed a little bit as well. Looking at those sources, we see a number of staining and wetting and mold growth areas up in that truss area. We do see some staining around a duct area that exited the exterior wall as well. So we had some poor sealant work along that condition. So what's causing these situations of moisture accumulation? Well, as Steve mentioned, it's pretty much determined, at least through our test work we've done, test openings, that these vapor retarder interruptions and lack of sealant and such openings creating these areas for air to transfer up into the space are really the culprit. And of course, hitting that dew point somewhere in that section there where that cellulose is at in that concealed space. As you can see in this slide, there are a couple of circles of red. That's kind of depicting this non-continuous vapor retarder, the oval, where the party separation wall of the vapor retarder is turned down the wall. Turns out that that wasn't sealed at the wall either. And then that other little oval circle, or little, more like a circle that's showing the penetration coming through the top stud, is basically a number of penetrations that were coming through, and they were unsealed as well. Here are some of the photographs of those conditions. Top one showing that non-continuous vapor retarder, plus all the cabling and things going through the unsealed opening in the stud. Bottom right, of course, very obvious, not sealed up along the ceiling penetrations. Similar to other types of penetrations in the top left. And on the bottom right shows that vapor retarder that came down onto the separation wall wasn't sealed against the wall. We also, in some cases, saw duct sealing not done, elbows not sealed, some insulation missing on some of the duct work, and that's not good either. That's certainly kind of adding to the entire flavor of moisture in that space. But that's also very important to be constructing correctly as well. And then to the bottom right, again, that's depicting that unsealed location of the duct exiting the building itself. We use a number of tools. Mostly we zero in on the WFI hydrothermal modeling tool to understand moisture accumulation in our assemblies as we evaluate folks that want us to do peer review work, and obviously evaluating our own designs as well. Steve talked a little bit about the traditional steady state modeling, psychometric chart. That dew point method is what we kind of grew up with, but it's really only one point in time modeling, and it's not able to really measure the storage capacity of moisture in the building system. So you can pick of course your coldest day of the year and run that dew point, and then find that maybe a couple weeks later it should be good, but it's still showing some moisture accumulation, where when we use a WFI model, we're able to see that through a period of time, through a period of hours, days, months, years, and see how that moisture moves in and out of that assembly. WFI it started in the mid-90s over in Germany, and it came across the United States in the early 2000s, developed a little bit deeper with Oak Ridge National Labs to better understand it according to construction materials we have in the United States, plus all the climatological conditions we run into. And of course, there's been models of WFI that have morphed since then too. So it's been around a long time. We have 2 trained WFI modelers on our staff that do work through these things quite a bit. And I think that's one of the key things about WFI is the ability to be sure you've got the right input in so you get the right information out and you're able to interpret that information carefully. The WFI models generate a number of different charts and graphs. That even generates a time film model that's really interesting to look at. So it does convey the information pretty good to the audience. And again, it's looking at all kinds of things, all kinds of graphs and charts about water content and relative humidity compared to dew point and all those things in the materials that you look at. It does take a while to set up, needs to be very accurate, and so it's not necessarily a cheap service and a cheap tool to run, because it does take some time to run through. Once you get a model set up, you can run variations of that very easily. but it's very important. And if you want to learn more about WUFI, certainly contact one of us about the WUFI scenarios and training and experience. We can be glad to help you with some more of that and talk more about WUFI. Don't have a ton of time today to talk about WUFI. But this is a WUFI model through the plywood surface, the plywood surface of one of those failed roofs. And as you can see, each one of these vertical lines represents a year, and the red line represents 19% moisture content in the plywood. That's really, as Steve mentioned before, is where you're at the point of maximum water allowable content, and things above that become problematic in terms of rot and deterioration. Well, about 30–40% of the year, in each year, this water content is way above 19%, traveling way up into the almost 50% range. So we've got very deteriorating conditions occurring here, and that correlates to what we found in our test openings. So now, how are we going to fix these situations, both from while they're in service and then maybe ahead of time in design? We're kind of starting to learn about this ourselves. We're on the leading edge, trying to understand the best opportunities. We kind of charretted a few ideas here, about 4 of them. The first 2 here on this page are interesting ones that we don't necessarily see as that viable, but they're worth talking about. And that is, first one, ventilating the truss space. Very common to do in steep roofs, of course, and very easy to do. We've got the natural low to high transfer of air, convection that works well, but we don't have that in a horizontal or low slope roof system. And we oftentimes have seen people try to do this, but it ends up bringing in more moisture, causing more problems than it does to remove the air and moisture that's there. So we just don't see that as a viable option. I think down the road there might be some opportunities to look at mechanical ventilating perhaps, but again, it's really tricky to do so, and now you're putting more roof penetrations through your roof as well. Constructing a complete vapor retarder, that's really, from the inside, that's really would be great. That's what we intended on doing on this whole business of poly vapor retarders in the ceiling, but it's just very, very difficult to do. We have seen cases upon cases where you just can't get that vapor retarder installed continuously, incomplete. And at this point, we're really not seeing that as a great option. Probably the one that maybe will get some attention down the road as far as new materials and new techniques, because it is a time to do it, as Steve was talking about constructing a new building. You're able to do that then and there and get that built after your roof is put in. So if it could be done and built better on the inside, that would be a good solution, but not now. We don't see this as a good option. So one option is to go from the top side down. This would be more roof replacement suited, just to the logistics that we were talking about. But you basically, have to tear your roof off and tear your deck off and evacuate the truss space concealed area, get down to the vapor retarder, and then layer a 2-inch layer of closed cell foam on top, then rebuild it all up again. Chart on the right, WUFI chart of the plywood surface, shows it to be very, very dry, very nice, very good condition. So this helps validate the fact that this has been set in the right location, this vapor retarder, and the resulting insulation above it to drive the dew point above the vapor retarder. Another option that we're a little more excited about and can be used in new roof construction and in roof replacement construction is working at trying to take that perimeter of the building and complete a vapor retarder bridge to a roof vapor retarder. We know how to build roof vapor retarders. Very straightforward, very easy to seal and work around. We know how to make the wall vapor retarders. Now the concern and the challenge is trying to bridge those two together in our construction detailing. Conceptually, that's the sketch on the right. We'll talk a little bit more about how we've done that on a couple projects to come. And then, of course, the WUFI model does show again that the plywood is in a good shape as we WUFI model that condition. Inside that truss space, that concealed space, you're now free to do, a couple different options. You can fill it up with fiberglass or cellulose. If you don't want to sprinkle it, you can compartmentalize to eliminate the sprinkler system and the insulation. And Scott will talk more about compartmentalization as he talks about his part of the presentation. And but now you've got this bridge and this continuousness around the perimeter, which takes care of being able to draw a line continually, not lifting your pen from the wall vapor retarder up along the leading edge of the spray foam, and then up into a connecting membrane. We've got a membrane coming around the plywood deck there. That's one concept, and then that connects to the vapor retarder on the roof. We now have a complete vapor retarder. So one of the case studies here is fixing one of these existing roofs. It was an apartment building in central Minnesota that had two apartment buildings on site. First floor was retail, top three floors were apartments. Of course, the investigation found all these problems. The owner wanted to start to look at repairing some of these problems before taking on a complete roof replacement project. After all, the building, I think at the time, was maybe 8 years old. So we looked at several options to help mitigate some of the more obvious concerns, and that was things such as they had the HVAC packs for the apartments didn't have good fresh air intake, so the RH was a little higher than it should be, so that got improved and dropped down to about 30-35%. They were able to go in and correct some ductwork that was leaking up in the truss space. They tried to seal some of the penetrations of the vapor retarder. A year later, we went out and did test cuts from the inside of the building, and lo and behold, the moisture had continued to accumulate. So we knew we could not do that type of repair anymore. We needed to go after the complete project. We looked at these two options that we just talked about, the topside complete vapor retarder approach, where you tear everything off and start from scratch on top of that vapor retarder. And we looked at the other one, which is the perimeter vapor retarder work. Talked about the pluses and minuses with the client, and they chose to go with the second option. It was just too risky for them to tear all this off and have this building exposed, as chunks of it needed to get taken care of at the vapor retarder level inside the building. And it was way too costly too. The cost estimates came in way higher. So going forward with that second option, or that bottom option on that page, to take care of that perimeter, this is a detail. It's kind of a schematic of the actual construction detail. And I think when you get this slide deck and you can blow this up a little bit, you'll see more of these components a little clearer. But our goal was to take off the plywood around the perimeter of the plywood deck. Of course, we had to pull the membrane back in the roof insulation, get into then that space, remediate anything we saw, clean it, get it ready, and then spray foam between the wall vapor retarder. And what we designed was a metal connecting bridge, a continuous metal connecting bridge to come up on the top side of the deck. Of course, once we cut the deck and bring a metal piece through the deck, we've kind of taken care of the structural integrity of the parapet, kind of cut the tendon, if you will, of the parapet. So our structural engineers had us go back and put some plywood on top of the vapor retarder system, and then some sheet metal angle work to reconstruct or resupport that parapet. So that's generally what had to happen all the way around the building. And it looks good in paper. We'll show you what it actually turned out to be. Before we do that, since we weren't tearing off the entire plywood deck on the building, we did want to go in and take a systematic series of cuts to understand what was going on in the field of the roof, make sure we got rid of any bad stuff in there, any kind of wet materials, any hazardous situations in there. We came up with a scheme to do test cutting. This was going to be ahead of construction, before the roofers started tearing off the roof. It also allowed witnesses from various sides of the litigation case to come out and take a look for themselves. And it also gave a good idea of what the roofers were going to come up with or be involved with later on when they started doing their tear-off work. And this is a diagram that showed how much of the areas got remediated and fixed and such. And it wasn't a ton of work done in the center of the roof. So, that was kind of our whole concern, is what if we start getting into this and we really should have torn the entire deck off. But we knew enough about what repairs had been done before to basically reasonably figure out that we could go after this through the perimeter. And it did turn out that that was good, and there wasn't a lot of deck replacement that was required on the project. Here's a couple of photos at the top showing those test cuts that were done. And I guess I forgot to say, I think there were 60 test cuts done a month prior to construction. And these things were then covered up each day, so you had a buttoned up roof at the end of the day. The picture on the bottom was one of the more center areas that was opened up during construction, and it shows you just how much of that area was inundated by moisture that had to be, you know, obviously taken out of there, the materials taken out of there, and then remediation done to stop any of the mold growth. So this is more of the impetus of the roof replacement challenge at the perimeter, where you go in and you pull back that membrane, take out that insulation, start cutting back a couple feet of plywood deck around the perimeter to reach down and get into that foam bridge construction work. Here's a little more of a close-up on the left showing that foam done and tied to the vapor retarder below, coming up and tied to the, we used a Z channel type continuous metal instead of a U channel. It turned out to be a better bend for the contractors and made more sense for installation. The bottom right shows again all that end wall work, all foamed up with a minimum of 3 inches to create that vapor retarder skin that makes it continuous from our wall to our roof. This photo on the top left shows the vapor retarder, the gray material, and it shows it kind of coming vertically and then a little bit of it sticking out beyond that plywood. Well, that's all one continuous piece that tied to the metal Z-girt, or Z channel, I should say, that was below. And then you're seeing the plywood in that upper left, and it's metal on top. That's the reinforcing plywood and metal to strengthen that parapet. That leading edge then of gray vapor retarder material, as shown then and on the bottom right, is where we tied into the main roof vapor retarder for the project. So now we have a continuous vapor retarder on the roof below and connecting to the Z, down the foam to the wall itself, vapor retarder, and doing the successful job of connecting all that. Then it became a relatively straightforward re-roofing project. You know, multiple layers of insulation and low-rise foam, staggered, slope to drain, 60 mil EPDM membrane, fully adhered, and then our metal flashings. We have been working recently on a new building that's being constructed. Actually, we got involved with the client at about 80% construction documents, where he saw some concerns about the potential wetting of the perimeter. He had seen one of our papers before on the subject. We got involved and started talking about looking at the options to work with the architectural team of their structural engineer on trying to create a complete vapor retarder at the building perimeter, similar to what we had done on the roof replacement project. We explored various options to do that, provided a number of WUFI modeling reports to supplement that and support that, and now the architect is developing final detailing for construction later on this year. These then are our slides of those options we looked at schematically, trying to figure out how to best tie that into the wall roof vapor retarder. First one, we ended up cutting the plywood deck in concept, and their structural engineers didn't like that. Again, this sort of takes care of that structural tendon problem with the parapet. The second one on the right, we started looking at maybe creating a marriage at the very outside edge by looping over the plywood deck that's installed, you know, a piece of self-adhered vapor retarder connecting to a metal continuous bridge. We did a WUFI model through that showed some moisture accumulation out on the outer edge because there wasn't much R value on the exterior wall at that location. So we ruled that out. Ended up going with this system where we kind of got back to, Steve was talking about a balloon frame. There's sort of a balloon frame concept going on here, but that's completely filled with closed cell foam. And that allows us to take that foam up and marriage into the continuous sheet metal bridge that's 90-degree bend there. And then we can tie that into our roof vapor retarder. So again, you can take your pen and start at the bottom, draw up all the way along, reaching all the way through onto the roof vapor retarder without lifting it, which is giving us our continuous and complete vapor retarder. Thought we'd end with maybe a couple things on what owners can do and architects can do. Probably could have a slide on what general contractors to do. We're getting a number of questions and call-ins from them lately, but you know, a lot of it is for owners to become familiar with, you know, their type of construction, especially if they're kind of thinking they may have something of this sort of vintage and this sort of construction sequencing. Maybe pay a little more attention to the roofs by walkovers, interior observations for mold, helping with that indoor climate maintenance, making sure you're operationally good with your packs, your HVAC packs, bathroom, kitchen fans are working, filters are clean, all trying to keep that RH down to try to avoid less moisture going up into that area of concealed space. If you see something, take early action, try to avoid what could be in a couple of years on maybe a couple of our investigations an actual roof structural failure. What architects can do, again, we're going to be citing right now on this vapor retarder bridge thing. I think that makes a lot of sense. Top side down maybe is one option. Perimeter, like we've done a couple of times, seems to make a lot of sense to us. And we're basically going back to vapor retarder 101 here, trying to make it continuous. And I think that's our challenge, though, is try to help that through all the construction materials where we get involved in our assemblies. Using WFI modeling is vital to help us understand that. We'd rather have doing this WFI modeling work during design versus having to do it later during investigations. But trained technicians, of course, are vital for anything that you want to really make sure gets done well. But you might want to consider other types of construction for the building itself. Could look at more concrete type construction, steel construction. Obviously, we're going to be changing up costs and other things according to that. Other types of construction in the concealed space lead to the compartmentalization stuff that Scott's going to talk about. That brings up another way to kind of minimize some cost, but you still should probably create that perimeter vapor retarder connection between the wall and the roof. That's still going to be vital even with a compartmentalization type of construction. So that's all I've got, and I'll turn it on over to Scott.
So Gary, I've got a couple of questions for you that might be interesting to people. It's sounding kind of like the choice that you and I are coming up with to suggest to people is to put the vapor retarder on top of the deck. Don't worry about what the foam or fiberglass is beneath. You may have to deal with it from a sprinkler, but at least you're not going to get yourself into trouble this way. We're going back to what sort of the old way was, if you will.
Correct. That's really what we're seeing is your topside vapor retarder is the place that you can best control that. And if you can make that bridge, that's really, we're in successful conditions that way, yes.
The other thing I think is venting, for whether it be dryers, kitchen vents, bath vents. We are talking, this is the main top floor that we're having the problems. But, instead of running them out to sidewalls, it might be a better choice to just go straight up with them. Yes, you have another roof penetration, but you can enclose those things.
I think that's another good idea to do as well. But yeah, you do have to be careful with, how many you are getting then on a roof and causing concerns with drainage and other things. But certainly organized, planned out, maybe even centralized, making some sense of those penetrations is a good option as well. But yeah, shortening that run, kind of minimizing the amount of potential problems you could have by ducts and turns and joints and all that go along with those vents. Yes, good questions.
Lot less potential leakage. So
yes, keep those opportunities down as much as possible.
Okay, thanks, Gary.
Yeah.
Good morning or good afternoon, wherever you are. Real quick about me, I'm a specifying engineer that was originally a sprinkler system designer. Currently, I spend a great deal of my time investigating fire protection system failures, not just sprinkler systems, but all kinds of failures. And that led me into these kinds of observations because of dry system or wet system failures in combustible concealed spaces. So this whole thing that we're talking about today is combustible concealed spaces, and there is fire protection that's required. Our fire prevention is really good. We do a great job. We don't have many fires, but if we did, we would find more of these kinds of failures or more of these kinds of problems because it is only the investigations that turn them up. So we do a great job of fire prevention, but we are seeing failures that are related, and we only find them through failure investigations. So how does the fire protection tie in? Well, I think both Steve and Gary have done a good job of talking about that today, but the building codes and fire codes generally require fire protection systems, and we're going to talk mostly about sprinklers today throughout the combustible construction. And it doesn't matter which building code you're in, and if we have international on this webinar, then theirs would also require some sort of sprinkler protection most of the time. Again, we tie into this because in our cold climates, if we have to put freeze protection in or sprinkler system in, we've got to protect it from freeze failures.
And we've got to protect it with dry systems, with antifreeze systems, heat, insulation, or a combination of those. Wet or dry systems and insulation or lack of insulation really becomes a problem for us. Too much insulation, not enough insulation, water-filled pipes in spaces that they shouldn't be, dry systems that we're going to talk about in a minute, all can be problematic. So if we talk about the alternates to the blown-in insulation, or vice versa, what can we eliminate if we do blow in the insulation? We've got the dry sprinkler systems that can be installed, and that's a system that's filled with compressed air or nitrogen. Antifreeze systems maybe can be installed. I'll talk about that in just a second. Wet sprinkler systems with adequate and appropriate insulation. The wet sprinkler system must have adequate heat. It's got to be more than 38 degrees Fahrenheit in every corner in attics and other concealed spaces. And I write that in here and talk to you about it because if the thermostat says 55 degrees because someone's left and gone south for the winter, 55 degrees is not going to be maintained in every corner of the living space, let alone in these concealed spaces that we're talking about. And keep in mind, we've been talking a lot about attics, but we have concealed spaces between floors too. And the same fire protection and the same insulation and the same failures occur in those combustible concealed spaces between floors. Non-combustible construction without fuel or loading or ignition sources. So if we can build a building out of metal and non-combustible materials and keep any fuels out of there, storage or anything else, then we've got an alternative. And NFPA has many exclusions, such as, and I've highlighted one here. You can go to the NFPA codes online and find this one specifically, but 815.126 is one of the exclusions that would apply. But I want to go back to the antifreeze systems just for a moment. Antifreeze systems are costly. They're costly to install. They're very costly to maintain. They have to be verified annually, and often they have to have the antifreeze replaced. And then we also have the problem that antifreeze systems for temperatures, Minnesota, North Dakota, South Dakota, many of the northern tier states have such a concentration of flammable liquids in them that they can contribute to a fire, as was shown in a Fire Protection Research Foundation study that you can get online also if you want to look at it. So antifreeze is not a good option, and it's no longer an option for living spaces. I have two slides here that show they're very similar to slides Gary and Steve put up, but this is showing tenting of a sprinkler system in a combustible concealed space, and it's the thermal lines or modeling of what the temperatures are in that space. And I only show this because this is something that needs to be done if you're going to try to conceal water-filled sprinkler piping in these spaces. So if an option is to blow it full of insulation, you're going to have to make sure that the warm air is going to keep that water-filled piping from freezing. This slide shows the penetration from the exterior of the cold temperatures. Now, it's really important that you understand this concept when you're coming up with your alternatives. This slide was based upon 70 degrees above the concealed space and 70 degrees below, and a minus 40 degrees exterior temperature. Often those interior temperatures aren't 70, they can be in the 50s or 60s, and often the outside isn't minus 40. But if we introduce a penetration into this exterior or outside wall enclosure, then those cold weather layer lines go even further into that space. And how far the cold penetrates or how much heat loss we have affects whether or not the sprinkler systems are going to, water-filled sprinkler systems are going to have a failure. Gary mentioned some alternates, and this is one. I've just put a slide on here of the 2010 edition of NFPA 13. That's what's adopted in Minnesota and will be for some time yet. The 2019 edition has a very similar section. It's just got a different section number because they revised the entire standard. But what you see here is an option for compartmentizing the truss space, TGI space, into small 160 cubic foot areas maximum, but the detail needs to be followed explicitly. One of the problems that we have with this is now you still have combustible concealed spaces, and if a fire can get into those spaces, then we do have fire extension concerns. Again, here's a little bit better picture of the same thing, concealed space with composite wood joist construction, showing the insulation along the bottom or the ceiling. It shows the sprinklers at the bottom, and then the sprinklers can be avoided inside this space. What's important here, though, is in design build construction, it's often overlooked that the sprinkler system design area has to be doubled or increased by twice the amount, because the fire can get in the combustible space and continue across where we don't have the sprinkler protection if there's any failure up there. That means double the amount of water necessary to protect a system. And in design build systems, that is frequently overlooked. My last bullet here, my guess, and it's just a guess, but it's an educated guess, is that the design build specifications overlook this requirement. And it is a significant requirement in residential and apartment type occupancies. So what kind of insulation related failures do we see? Well, freeze failures are very frequent, failure types that we see quite often. Floor and ceiling spaces are filled with insulation. The water-filled pipe is installed too close to exterior walls, insulated or away from the heat. The rim joist is not properly sealed and insulated. Exterior penetrations aren't properly sealed. All of those lead to air and moisture that gets in and causes our failures. And the very bottom picture, well, the middle picture is a freeze failure of a water-filled pipe, and the bottom picture is ice that was actually removed from CPVC before it actually failed. So we want to avoid the insulation-related failures. Tenting, I already talked about. This slide shows a roof that was removed. It was actually a one-year-old roof when the failure began. There were no as-built drawings. They had to take the ceiling, the roof off, open it up, and then follow the pipe. As they followed it, they tented it, which is just really putting bad insulation over the pipe, attaching it to the ceiling. But it has to be sealed completely, and it has to be for the life of the sprinkler system in the building. One way to avoid it and still blow up the area full of insulation. So that's what's showing here. They were tearing it off, a brand new building, upscale condominiums, and you have to locate the pipe and then remove all the insulation that's in there, tear it off, and redo it. Dry systems can certainly lead to failures, and that's something I see way too often. This is corrosion in dry systems. Dry systems are with schedule 7 to 10 pipe are lasting 7 to 12 years when I see failures. Is corrosion, the corrosion in these systems can lead to a sprinkler system not operating when it should, or a freeze failure, or water loss, or both, and that's what we see frequently. So as a design team, as an architect, as the engineers, if you've got contractors on board, you've got to look at what's the best option for the owners. And design build is not necessarily the best option for the owner when we're talking about the problems that we are in this webinar. Not just the sprinkler system problems, but how do we overcome them? How do we avoid them? What are our options? 7 to 12 year life expectancy I'm seeing with the schedule 7 to 10 dry systems, freeze failures due to improper installation, freeze failures due to corrosion, corrosion failures, failure to maintain the systems. How do you maintain these systems in attics or in that space? And clogged pipes and sprinklers can be a real problem in a fire scenario. It costs more to do it correctly with the dry systems. You really need to have the team approach. We need the whole team looking at it. We can't put a design build spec out that just puts a low bid NFPA 13 minimum system together. Design build sprinkler systems in unheated attics are not appropriate for the long term of the building. It's just not the best. You can give some minimum standards which you need to provide, but just design build would not do it. There are options, but you won't get them from the typical stamped design build specifications that we see. So these systems that we're talking about, we need some sort of fire protection. They are life safety, property protection, and we often overlook firefighter safety systems. This is a building that was a baseball park. It had a dry sprinkler system in the attic, and the dry sprinkler system had corrosion issues. And as you can see, it literally burned to the ground on the first base line from home plate to the first base. So we have to look at how do we provide the proper fire protection and still avoid the issues we're talking about today. Performance-based design is certainly an option, but you'll need an engineer and an architect to be working together, and I would like to say a fire protection engineer to bring all these possibilities and probabilities together. Finally, this is another fire slide. See, this is a roof that's been burned off. This is a fire last year. There's no fire stopping, no fire protection in this attic. We need to do a better job of protecting these ceiling, attics, and spaces that are combustible that we've been talking about here today. I guess I'll pass it back to Steve right now for any questions, and we'll go from there.
Well, thank you, gentlemen. And again, we apologize for the technical glitches earlier. We will continue to take questions if anybody has any, so please, type them in, and we'll do our best to answer. Well, once again, thank you for attending today's webinar. Just as a reminder, we will be sending out an email shortly after the show containing the recording of today's presentation. CEUs will be delivered in a separate email to participants within a week. So please keep your eyes, and maybe your ears on your mailbox for future webinars. If any more questions do come to mind, you can reach out to our panel at their respective email addresses on the screen, or simply visit our website. Have a great day.